In this video, I introduce VICReg, variance-invariance, covariance, regularization for self-supervised learning. Self-supervised learning learns image representations by maximizing the agreement between embedding vectors produced by encoders fed with different views of the same image. One of main challenges is how to prevent the encoders producing constant or non-informative vectors, namely collapse. There are three popular approaches to preventing the collapse, namely contrastive method, quantization-based method, and joint embedding predictive architecture as shown here. This contrastive method, this quantization-based method, and this joint embedding predictive architecture. VICReg is the self-supervised learning method that avoids the collapse problem using two regularization terms in two-branch embeddings separately. Namely, one, a variance V term that maintains the variance of each embedding dimension above a threshold. Two, a covariance C term that correlates each pair of variables. The loss function z, as shown here, minimizes the mean square distance between the embedding vectors. Here is the architecture of the VICReg model. This input image batch, this branch A and this branch B. We use the loss information S to train the model with two regularization terms V and covariance C. Since the variance and the covariance terms applied to both branches separately, VICReg preserves the information content of each embedding at a certain level and prevents informational collapse independently for the two branches. VICReg is based on joint embedding predictive architecture with no shared structure or parameters between the two branches. Practically, the encoders with identical structure map the input image as latent representations, and the expanders are used to eliminate the information by which the two representations differ and to expand the dimension in a nonlinear fashion so that the decorating the embedding variables will reduce the dependencies between the variables of the representation vector. After pre-training, the expander is discarded and the representations of the encoder are used for downstream tasks. Given an image I sampled from a dataset D, two transformations T and T prime produce two different views, X and X prime. The overall loss L is computed at the embedding level on Z and Z prime, as shown here, which includes three terms, namely invariance term, variance term, and covariance term. The last two terms are used to prevent the collapse, where lambda, mu, and kappa are balance weights. Zi and Z prime are batches from T and T prime. The images are processed in batches, and the two batches Z and Z prime are composed of n vectors of dimension D, and the vector Zg is composed of each value at dimension G in all vectors in Z. The variance regularization term V is defined as the hinge function on the standard deviation of the embeddings along batch dimension as shown here and explained in this figure. Where the regularized standard deviation S is defined as here, and gamma is a constant target value for the standard deviation. This criteria encourages the variance inside the current batch to be equal to gamma along each direction, preventing collapse with all the inputs mapped on the same vector. However, if S select to be variance in the Henge function, the derivative of s with respect to x close to 0 when x is close to its mean value. Therefore, the gradient of v becomes close to 0 under the embeddings class. The covariance matrix of Z is defined as here and shown here. The covariance regularization term C is defined as sum of the squared of diagonal coefficients of C with factor 1 over d as shown here. This term encourages the diagonal coefficients of C to be close to 0, decorrelating the different dimensions of the embeddings and preventing them from encoding similar information. The invariance criterion S between Z and Z prime is defined as the mean squared Euclidean distance between each pair of vectors as shown here. For more details, please check with these references. Thank you. Bye.